Welcome to RN Talks Maths. Today we are going to discuss Introduction to Integrals, an age-old topic. Founding father Sir Isaac Newton. Calculus is an amazing part of maths, a field of maths. Now see, suppose we have a function whose graph on the xy plane is like this. Let's say this is y equal to g of x, the curve of g of x. And this g of x function is to be observed from, let's say, x equal to a till x equal to b. For finding the area, what we need to find is the area bounded by the curve of g of x equal to y above x-axis and between the ordinates. What we mean by ordinates is the lines parallel to y-axis. Between the ordinates x equal to a to x equal to b. Let's say this is what we call as capital A. Then this is the area. Let me shade that area. This area is to be calculated. If this curve would have been straight line curve, then we could have got geometrically simpler areas to calculate. Now since this is a smooth curvature having changes in slope, then we cannot use direct simplified geometrical figures like rectangles or triangles or trapeziums, etc. What we can do here is then we can divide this entire area into strips. Now the problem with the strips came up when we took a very wide strip. Let's say this is a very wide strip and defined from, let's say, x equal to x from x till a further position. We define the width of the strip as h, let's say. So this position is x plus h. Now what is this h? Let's say capital A is the area to be covered. H is the strip width. We define h as the strip width, the width of the strip. Now here we have this height as g of x and the height here is g of x plus h. For a function which is rising, the values of g of x and g of x plus h will definitely have a delta y. And therefore, when we define this strip as a rectangular strip, either with this as the height or with this as the height, we have problems. What is the problem? Let's say we define the rectangular strip with the height of g of x, then this is the triangle we are going to miss. And if we define this strip with the height as the upper height or the higher height as g of x plus h, this is the triangle which will come in excess. Now here is the problem. And what I wanted to do actually to calculate the area, I wanted to have many such strips. Many such strips. And each time I would have a choice of either a lower height to be taken or the upper height to be taken. And you imagine each time I'm going to make an error. Now here was the problem. The error could be reduced. The error could be reduced if you could reduce the area of these triangles. And for that, we need to consider the area of the triangle, and triangle's area would be half into base into height, and therefore the area of the triangle would turn out as half into h into g of x plus h minus g of x. This big calculation could be reduced to 0 if suppose this h, that is delta x, which we define as h, this delta x which we define as h, if that is taken very small, if this goes to 0, then this delta y would also go to 0. So here I write, if h is very small, then delta y goes to 0, and therefore this delta doubly goes to 0. Why so? H tends to 0 as well as delta y tends to 0, and the problem of either an excess of a triangle or a deficit of a triangle would be a minuscule error. This becomes a insignificant error in area calculation of the strip. Now it becomes insignificant, and that means if this h is very small, the strips are very thin, hair thin strips. Yes, very thin strips. Now the problem came with the number of strips. Now how many strips were we supposed to have? Let's say this was 1, this was 2, and like this we numbered, and then we said that let there be n strips. So n, here is another variable, n is equal to the number of strips. So if n is equal to the number of strips, it must have some count, and that count can be obtained as equal to the width of the total domain, that is b minus a, divided by each strip width. The moment you had this with the limit of h tending to 0, this was tending to infinity. This entire ratio was tending to infinity. That means n is tending to infinity. The number of strips is very huge, large, and therefore we are going to have an infinite number of strips here. Now, that way speaking, let's say we position the places like this is a plus h. This position would be a plus 2h, and let's say this is some rth strip here. This is some rth strip. That means this position could be written as x is equal to a plus rh. A plus rh as a position would create this height as height of g of a plus rh with a minuscule error either in excess or in deficit. The way you calculate the height depends on that. Now here we are having a series of strips, and the strips areas would be like adding rectangular strip areas with minimal error. So here we go with the calculation that this particular A, the area bounded by the curve of g of x above x-axis between the ordinates x equal to a to b, this capital A as area under the curve. In short, we can write area under the curve would be equal to a summation of the strip areas, let's say AI's, from I equal to 1 till n, where n tends to infinity. So that means if you define AI for any particular strip, let's say if I define AI for this strip, if this is a strip to be defined, let's say like this, how would we define this? A rectangular strip with this height into base width of h, so into h. This can be defined as the rth strip area. So we can define this as the rth strip area. So this can become the r equal to 1 till n, of course, theory by Rn. Now, summation of r equal to 1 till n on AR with a limit of n tending to infinity can result into something interesting, and that can be looking like this. Limit n tends to infinity on a summation whose suffix is r is equal to 1 till n applied on the area of a strip, a rectangular strip with this height and this base width, is g of a plus rh into h. Height into base width, a rectangular strip. Such many strips areas are added with a limitation of n tending to infinity. How complicated this could have been, can you imagine? In the pre-Newtonian era, this was a practice for the mathematicians to calculate the areas of the strips by plotting those curves, like let's say log x curve or sin x curve, plotting those curves and then calculating the areas of the strips and then adding them and then calculating the area would be a momentous task. Very tough. Sir Isaac Newton gave here an amazing simplification. First of all, he simplified the symbols. So Isaac Newton said that you are summing up. You are having a discrete summation here. So when you have this summation with the limit operator, why can't we do it like this? Let's say this summation operator with r equal to 1 till n with the limit of n tending to infinity be all together replaced by an s from r equal to 1 till n. Why can't we do it like this? And almost all the people there agreed. Then he said that what you are referring here is a plus rh as an rth position on the domain variable. Why can't we define it by a simple x? So a plus rh suddenly become an x. And he said that, what is this h? This h is a small change in x. Then how about we calling this as a dx? H as a dx. So that h became all of a sudden dx. And then it went a revolutionary change. This suddenly converted to an s, means a continuous summation of r equal to 1 till n on g of x dx. Then came the final revolutionary change. Sir Isaac Newton said that, see, this is now a function of x with small changes in x multiplied. This becomes the height and dx becomes your base width. Then what is this r and n doing here? What is Rn doing here? He must have exactly asked like this, and it would have been funny. I would have enjoyed that moment had I been there. Now seriously, he said it. And then, here it comes. He says that this must be representing some value of x. That is, at the first strip, it begins with x equal to a. So why can't we replace this with x equal to a? And then when you go till the nth strip, it becomes at x equal to b or maybe b minus dx. We can replace this upper limit by b, maybe x equal to b. And all the people agreed. This agreement was becoming increasingly popular, and people started using this idea because the ideas of differential calculus were already in place. So it was, you can say excessively used, and this symbol went in a genetic, I would say a genetic elongation like the neck of a giraffe. And it become a symbol like this with lower limit a and an upper limit b, which we today call integral of g of x dx from lower limit a till upper limit b. This is of course a limits on the variable x, and this is what we call as a definite integral. Now, definitely, we are not going to discuss or stop our discussion right here. This is going to be a definite integral as just an introduction. We are going to continue on this. We are still a long way to go. Now, integral a to b g of x dx is equal to a definite integral of g of x function. Then people asked, what would be the evaluation? How would the evaluation be? And then the differential calculus was used. was used. So I would like to make some space over here and then proceed with the further calculations. Now see, how we can relate this to the ideas of the derivatives is something like this. Uh, g of x function, if it is, let's say, what I should say, the velocity function. If it is, let's say, a velocity function, then it must be the rate of change of some displacement. And if it is the rate of change of some displacement, then it must have some primitive. So let your g of x dx or g of x function be the derivative of some fx function. Let this happen. That means g of x is the velocity function, fx is the displacement function, x is the time. So ds by dt equal to velocity means v dot dt equal to ds. That means we can take this dx along with this gx and create a d of f of x. The moment we have it like this is on a continuous basis. Now, if we turn this to a small change, or let's say non-infinitesimal change, a significant or a large change, then we can write g of x into delta x would be equal to delta of fx. That means a summation of this would be equal to the summation of this. And summation of this from r equal to 1 till n can be equal to r equal to 1 till n. The same process that we were having earlier. And then a sum of small changes. I will write here. Sum of small changes can be equal to a final change. If it is equal to a final change, we can say the final change can be like from f of b, from f of a till f of b, and this can be the summation on delta f of x from r equal to 1 till n. This can be the net change. So this summation which became this can be alternately written as equal to f of b minus f of a. This can be written, this can happen. If and only if this happens, this is true, if and only if ddx of fx is equal to g of x, only then this can happen. And hence we are fortunate to calculate the integral of g of x dx from lower limit a till upper limit b, given this value is available with us. So I'll write it bigger. This is a grand calculation, and this is like f of b minus f of a, and this is how it goes. So my idea here is that let's say we define this lower limit a as some arbitrarily fixed position, and let's say it's not fixed actually. So let a, now I will define something else. Let a is an arbitrarily fixed initial point. And what is b? Let's say b goes to an indefinitely variable final position. Then the point is, if that happens, are we really having any limits on the calculation, any definiteness of the calculation? The answer is no. And that leads to a concept of integral g of x dx. Now, without limits, these would be the meaning. the initial point would be arbitrarily fixed and the final point would be indefinitely variable. That is what we call as the indefinite integration. In the indefinite integration, what about the result? Then we can say this final point is as good as, writing any x. This can be as good as writing any x, so that can be an fx. This f of b can turn to f of x. And what about f of a? We can write this as an arbitrary constant. So therefore, in indefinite integrals, we can write f of x plus c. This c is an arbitrary constant. Arbitrary constant. But definite integral does not require any arbitrary constant, because it might be, you can say defensively, you can say that the c gets cancelled from the upper side as well as from the lower side. Well, this was definitely introducing definite and indefinite integrals. Thanks for your patience. Stay subscribed. We'll get back with more surely in a short time. See you in the next lecture.